Hey there, in this video we'll be looking at Charles's law. Let's get into a quick definition. First things first, Charles's law states that the volume and the absolute temperature of a gas are directly related. That means if absolute temperature were to go up, volume would also go up, and if absolute temperature were to go down, volume would also go down. It's a direct relationship. And this relationship assumes two things. It assumes one, moles. So that's the amount of gas. So amount of gas, you can think of it as the number of gas molecules in a sample. So the moles of gas and the pressure. So whatever units you may use, whether it be kilopascals or psi, pressure also remains constant. So to summarize, volume and absolute temperature of a gas are directly related if the amount of gas in a given sample and the pressure of that sample remains constant. Awesome. So here, let's look at a graph, and this shows the direct relationship of the volume and temperature, right? So as volume is on the x-axis, it's the independent variable, and volume increases accordingly. Now, a really important part that you see over here is the units for temperature, and this relates back to the definition over here. I'm not sure if you guys noticed it, but this term, absolute temperature, is very important, and it refers to the Kelvin scale, right? On my channel, I already have a 4-minute video on what the Kelvin scale is and how we use it, so that may be of interest to you. But if you don't have time to watch that video, all you need to really know is that a Kelvin is a unit of measurement that's derived from Celsius, so that Kelvin equals degrees Celsius plus 273. And whenever we do calculations with Charles's law or any of the gas laws, we're going to use Kelvin temperatures, not Celsius temperatures. All right. So now let's go out and check out a cool example to remember Charles's law. And the example I'm going to use for this video is a basketball. So if you leave a basketball outside on a really cold day, right, say these are clouds, it's really cold outside, like negative, 20 degrees Celsius. In this kind of weather, what happens to the basketball, and you may have observed it if you play basketball or any other sports with ball-like equipment, the volume of the basketball goes down. And this is a consequence of the temperature. So since the temperature went down outside, the volume of the ball goes down. The basketball deflates, right? And this is the same with a football, a soccer ball, everything. The temperature outside forces the volume of the ball to deflate. And the same way, if the temperature were to increase, say, it becomes a sunny day, right? Lots of sun. What would happen is that the temperature would increase and the volume would actually increase. So for those of you guys who have experience with using soccer balls or basketballs, this is a really cool way to remember it, and you can try it for yourself if you leave a basketball or a soccer ball out on the front porch. Alright, so now let's get into the equation and how we derive the equation. If I were to divide the volume of, say, the basketball by the temperature outside, I would get a constant value, right? This is because, well, this is a direct relationship, as we explored over here. So since you get a constant value from this, what you could also do is that if you were to change the volume and the temperature of the basketball while keeping N and P the same, you would end up with a new set of conditions. So like a volume 2 and temperature 2, right? And if you were to divide this, it would still equal that same constant value because it is a direct relationship. Now, if I were to combine both of these expressions, what I would get is I could just equate them to each other. So V1 over T1 is going to equal V2 over T2. And this expression is what we use to solve problems when it comes to Charles's law, and it is the equation associated with Charles's law. So let's do some practice problems with this expression. Okay, practice problem number 1. Pennywise the clown wants the volume of his balloon to get bigger so he can scare more kids. If the balloon has an initial volume of 2.3 liters at a temperature of 16 degrees Celsius and he increases the temperature to 28 degrees Celsius, what is the new volume of the balloon? Now this is obviously a reference to the movie It, if you didn't catch that, the clown at least. And what we can do here, and what I like to do for all of these problems, is kind of sort out what we have given to us, right? We have the initial volume of the balloon. Whenever you hear the term initial, you know it's going to correspond to whatever the initial volume is, like the V1 or whatever one subscript there is. So it's going to be 2.3 liters. Right? We also know that the initial temperature is about 16 degrees Celsius. Now, 16 degrees Celsius is not helpful whatsoever. We need that temperature in terms of kelvins. And as we explored earlier, 16 plus 273 will give you the degrees in kelvins, which in this instance, doing some quick math, should be about 289 kelvins. Okay? And finally, we're given that he increases the temperature 28 degrees Celsius. So that's going to be T2. That's going to be, same thing here, we cannot use the Celsius value. So 28 plus 273 over here is going to give us, some quick math, 301 kelvins. All right, and we're trying to solve for the new volume. So whenever you hear the term new, it's going to be V2, or the second volume, right? So how do we use our equation to help us solve this? All right, so one of the things that I like doing when it comes to these kind of problems is kind of solving the equation earlier. So like kind of isolating for the variable you want to solve for. So here's our expression. So V1 over T1 is going to equal V2 over T2. Now what you can do is you can multiply both sides by T2. So you get V2 is going to be equal to V1 over T1 into T2. Right, so I multiply both sides by T2. Right, this is going to cancel out, and you're left, this is a multiplication, so you can just put that top over here, and this is our new expression. All right, now that we have this new expression, it's just a matter of plugging in numbers and seeing where it takes us. So you're going to have V2 is going to be equal to V1, which is going to be 2.3 liters, over T2, which is going to be 301 kelvins. Make sure it is T2. That is very important. Over T1, which as we mentioned earlier is 289 degrees Kelvin. All right, so the units of Kelvin is going to cancel out, which is good, which means our answer is going to be in terms of liters, which is going to be appropriate for volume. And if you do the calculation here, you'll get approximately 2.39, which we're going to round up to 2.4 for significant figures. So 2.4 liters is going to be our answer here. All right, so does this make sense? As you mentioned earlier, it was a direct relationship between volume and temperature. And in this instance, he increased the temperature to 28 degrees Celsius. That means the volume is going to increase. Initial volume was 2.3. We got 2.4. Therefore, 2.4 is V2. All right, let's try one more problem. Okay. Problem number 2, at a temperature of 20 degrees Celsius, Tom Brady's football has a volume of 0.6 liters. If the ball is left outside so that the new volume becomes 0.8 liters, what is the temperature outside? All right, so same idea, we're going to give what is given to us. Or sorry, we're going to write down what is given to us. So first we have that the temperature, the initial temperature is 20 degrees Celsius. So we know that T1 is going to equal 20 degrees Celsius, but we need that in kelvins. So 20 plus 273 is going to equal 293 kelvins. And then we know that the initial volume is going to be 0.6 liters. 0.6 liters. And we know that the ball is left outside so that the new volume, so the keyword new there, V2, is going to be equal to 0.8 liters. So the first time the air in Brady's football actually went up for a change. And now we're looking at the temperature outside. So what is the new temperature? So T2. All right, and this is going to be our unknown value. So same thing we did last time, we're going to manipulate the equation so that we get T2 by itself, and it's just a matter of substituting in numbers, which makes our job a lot easier. All right, so here's our equation, V1 over T1 equals V2 over T2. What we're going to do here is cross multiply. You're going to get V1 T2 is going to equal V2 T1. We're trying to solve for T2, which means that to divide both sides by V1, because this will cancel out. And we're going to be left with T2 is going to equal V2 T1 over V1. Now it's just a matter of substituting in numbers, which we love doing. So it's going to equal V2. Our answer for V2 is 0.8 liters. Just try and make sure you put in the right value for the subscripts. It does get confusing at times, and it may result in a wrong answer. So just double check, make sure you're putting in the right one, like when it comes to V2 versus V1. And then temperature, 293 kelvins. And then we're going to put that, this is liters, sorry, over V1, which is going to be equal to 0.6 liters. All right, liters cancel out, which means our final answer is going to be in terms of degrees Kelvin, which is perfect. Sorry, in terms of Kelvin, which is perfect because we're looking for temperature. If you do the math over here, you get roughly about 390.67 kelvins. And if you want to convert that to degrees, you can just subtract by 273. You'll be left with about 117 degrees Celsius. Now let's make sure that our answer makes sense according to Charles's law. So what we can do here, sorry about that, is we saw that the volume increased, which means temperature has to increase as well. Initial temperature was 20 degrees Celsius, final temperature is 117 degrees Celsius, so obviously the temperature increased, so our answer does make sense. So in this video, we looked at Charles's law, we looked at definitions, we looked at graphs, we looked at examples, we looked at how we can derive Charles's law, and we went over a few practice problems. If you found this video helpful, please consider liking the video and subscribing to the channel, and I can't wait to see you guys for the next video.